So we have ICMP abuse cases today. So as you guys all probably already know, ICMP is the network's error reporting system, and it's also one of the most consistently abused protocols in the attacker's toolkit. Not because of a single flaw, but because its designs make certain abuses structurally inevitable. So this session is going to cover 8 distinct attack classes. And remember, every technique here has a MITRE ATT&CK mapping, a detection IOC, and a mitigation. That's sort of the analyst mindset that we're building here today. And before we get started, does everybody have Wireshark and Nmap installed by any chance? If not, it's okay, because we can just go through it together. I'm just curious.
Yeah, I have.
Cool. Well, if for those of you who don't, you may want to look into installing it just for upcoming scenarios and things coming up in later on sessions. But for today, it's not a big deal because we can just go through it together, kind of like last week, if that works. Okay, so we've got, like I said, eight topics. We've got, I'm just going to go through them really quickly, and then we'll go through them individually, kind of. So we have ICMP, type and code mechanics. That's the first one. Network reconnaissance, so like ping sweeps. And then we have the ping of death and ICMP redirection attacks, ICMP tunneling and exfiltration, and then Smurf attacks, PMTUD manipulation, and OS fingerprinting via ICMP. You'll notice that these attacks span the entire engagement lifestyle. So like type 8, it starts with recon, redirect and tunneling appear mid-intrusion, PMTUD abuse, which is a persistent disruption tool, and then OS fingerprinting is reconnaissance that enables everything else, essentially. So if we get to it today, hopefully we do. While my mouse isn't working properly, you'll have to bear with me, guys. Yeah, if we get to it, we're going to have a lab and a quiz to follow. And why I asked about the Wireshark and Nmap is because we'll physically execute a ping sweep, and then we can analyze the traffic in Wireshark if we have time. But if we don't, then I might just do like last week and just post it, and you guys can check it out. You'll have to bear with me. I'm not feeling the absolute greatest today, so if I'm a little sluggish, that's probably why. I apologize in advance. Okay, so before we talk about the attacks, you need to be fluent in header fields. So like every ICMP abuse technique targets one or more of these fields specifically. So in here, we have type 8 through type 0, or type 8 and type 0 are the ping pair. They're fundamental to recon and tunneling. Oops. See this mouse, I'm telling you. It's going to be thrown out the window today, maybe. It put us way ahead here, didn't it? Okay. So type 8 and type 0 are the ping pair, which are fundamental to recon, like I said, and tunneling. And then type 3, the something failed message, basically. There's 16 different codes. Each leaks a different network intelligence. Type 5 is the redirect, designed for routers, abused for man-in-the-middle attacks. And then type 11 is the TTL expired. Traceroute uses this to map hop by hop topology, basically. So let's say an administrator looks at a type 3 code, type 3 and a code 1 and thinks that host doesn't even exist. And an attacker looks at a type 3 code 1 and thinks, I've just confirmed that IP is unallocated. And I now know the perimeter isn't blocking ICMP errors, right? So that's kind of the two different mindsets there for that and how the attacker will think versus what the defender will think. So which type would you generate by running a trace route? Does anybody know? If you, if you were running a trace route, which type would be generated?
The hops.
It'll be, let's see. No, I don't think type 11, I believe. TTL exceeded. Each router's decrements TTL and sends back 11 /0 when it hits 0. So type 11, right?
Oh yeah. So you're talking about the type and code. Okay.
Yeah. And then the data field right here, this becomes the attack surface in the tunneling, essentially, right here. Okay. So network reconnaissance, so ping sweeps. I don't know if you guys can hear the chickens, but I'm sorry if you can in advance because they're a little bit loud right now outside. We have MITRE attack, T1018. This is remote system discovery. So for anybody that does have their Nmap, their terminal open or Nmap, you can go ahead and run this scan right here. I don't know if you can see it or not, but this right here. And it'll show you, well, you know what? Hang on a second. I can't. Let me do it this way. Just give me 1 minute here, guys. I think I know an easier way. I'll just do it. Can you guys see that? Are you still seeing the same screen?
Yes.
You can see my terminal?
No, only
No,
the slides.
Okay, perfect. Just give me 1 second, guys. Bear with me here. Eventually, I'm going to learn how to use this properly so that I don't have to keep closing one window and going to another one. Well, I will do my homework on that this week, and I'll be better at it next week. You'll see. Can you guys see that? The terminal now?
Yep.
Perfect. So you can
Yes.
see here. You can see here that I ran Nmap, and then I did -SN 192.168.1.0-24. And then you can see the output here. It shows starting the Nmap, and then the stats, and then it shows there are 256 IP addresses with 0 host stop, and that it took 209.22 seconds to finish the entire thing. So, okay, 1 minute here. Like I said, next week I'm going to learn how to do this a lot better.
What's the IP address that you use?
That was just a.
Is that your network IP?
Yeah, I think that was my
That-
own.
That's
Yeah,
the
that was
network
mine.
address.
That's my IP, but it's a sandbox essentially. Like it's not anybody's. It's just
okay.
my own. It's my own. It's It's not anybody's but mine. I wouldn't use anybody else's but my own for these things.
So basically, ping sweeps is like checking the network, who's online or who's available on the network,
Exactly.
right?
Exactly. That's exactly right. It's just to see who's awake and who's going to respond, and you know. Okay, let me go back to this right here. I swear I'm going to be better at this next week. Okay. So this what you guys just saw is always step one. So before an attacker touches a single port, they want to know which IPs are alive, like we were just saying. So a ping sweep answers that within seconds. Sometimes a couple of minutes, depending. So the Nmap command box, what we just did, the -SN means no port scan. So you just pure host discovery. You're not really concerned about ports at that point. You're just wanting to know the host, like we said. Nmap sends ICMP echo request and TCP SYN 443 and TCP ACK/80 by default. So even if type 8 is blocked, Nmap may still find live hosts via TCP, which is why blocking type 8 alone is not sufficient defense, right? So I'm going to ask you guys, why do enterprises block type 8 inbound at the firewall if attackers can just switch to TCP probing? Does anyone know? Anyone have any thoughts on that one? So why do they block type 8 inbound at the firewall when an attacker can just switch to TCP probing? What would be the methodology behind that? Does anyone know? You guys hear me?
Yes, I can hear you.
Okay, cool. Just making sure. So basically, it's because it forces noisier techniques that generate connection tracking logs, which makes detection easier, right? Essentially. So if a threshold of 50 echo required per second is a starting point tune based on the environment, internal network baselines will vary. The key signal is sequential addressing and high rate plus no corresponding. So the TCP UDP sessions from the same IP, essentially. Okay. Second, I think we have somebody else trying to come in now. So we'll go on to the next one here. So ping of death. This is the oldest attack in today's session, and it dates back to 1997. And I'm only going to include it. Well, I'm including it not because you'll encounter it on modern Windows, because you won't, but because it teaches the single most important principle in protocol security, which is always validate inputs before acting on them. So we'll do the math here on this. The maximum IP packet is supposed to be 65,535 bytes. That's right here. An IP header is 20 bytes. ICMP header, 8 bytes. The maximum legal ICMP data is 65,507 bytes, right? An attacker sends fragments that reconstruct to greater than 65,535 bytes, which is an illegal total, but each fragment is individually legal. So the flaw basically is that the operating system didn't check, will this reassemble to something too big before allocating memory? the overflow wrote into adjacent kernel memory, which means the whole thing's going to crash, right? And the modern relevance of this is that this is the part that matters for, like, this is the part that's going to matter in your careers, I would think, is any embedded device running a legacy or vendor proprietary TCP IP stack may not have been patched. So basically anything that's running legacy or anything like the older, you know, may not have been patched. So you may one day see something similar to this. It's a good thing to keep in mind anyway, because it does go back to the basics like we were talking about a little bit last week too. Okay, and then we have the ICMP redirection attacks. This is MITRE attack T1557, which is adversary in the middle. This attack is actually kind of elegant because it abuses a legitimate network management feature. Type 5 redirect was designed to let routers optimize routing. And the attacker just basically sends one themselves. So step 1 is normal traffic flow from the victim to the gateway to the internet. Step 2, the attacker, who's on the same LAN, LAN, sends a spoofed type 5 code 1 appearing to come from the gateway. And it says for traffic to whatever the IP address, use this IP address instead. So the victim's kernel updates its route cache and starts sending that traffic to the attacker, basically. It's pretty slick. The critical point of all this is the attacker then forwards the traffic to the real gateway. And the victim never does lose connectivity, so they don't have any idea that anything is even happening. The attacker reads or modifies every packet silently without it even being known, without the victim even having any idea. So real world context of this is this attack requires LAN access. So it's essentially an insider threat, post initial access technique. And if an attacker has already compromised one device on a VLAN, they can redirect traffic from every other host on that same VLAN. So how would you detect this without an IDS? Do you guys know? Any thoughts on that one? How you can detect it without an IDS? No ideas on that? No thoughts?
Yeah, unusual traffic, maybe, or like if they try to navigate through the network and uses your IP address from a specific network or VLAN, then probably there are some behaviors that you could observe, like lateral movement of the packets.
Yeah.
Probably from the
Yeah.
firewall logs also you can detect that.
Right. You can check the victim's routing table too, right? With IP route show cache or netstat R, which is more Nmap commands, because an unexpected next hop IP for a common destination is the tell. So basically what you were saying, it's essentially the same thing, but you can use netstat or on Nmap to be able to tell. So I think we're all right in there. You're all right. On the right track for sure. Okay. And then we have ICMP tunneling and exfiltration. This is MITRE attack T1095, which is a non-application layer protocol. And T1048 or 0.003, which is exfiltration over an alternative protocol. So this is one that surprises most junior analysts most of the time. The firewall is passing ICMP. The IDS is not alerting, and data is leaving the network inside ping packets. Okay. So a normal ping data field is 32 bytes of OS pattern, right? The tunnel data field is up to 1400 or more bytes of encoded payload. That's a TCP connection, a reverse shell session, or a file chunk, right? So these are some names of some tools that you guys will probably become more familiar with, but definitely something that you need to be familiar with. And they are, we recognize them as threat intel. So we have ICMP tunnel, which wraps complete IP packets inside the ICMP. Hold on a second, guys. I think we have someone else coming in now. 1 minute. And I swear, I promise you, by next week, I'm going to be doing this a lot better, a lot more smooth. Okay, so we'll go back to here. Normal ping data field is 32 bytes of operating system pattern, right? The tunnel data field is up to 1400 bytes or plus bytes of encoded payload, which is a TCP connection or a reverse shell session or file chunks, right? So we know that. And then the tools here. Again, the ICMP tunnel wraps complete IP packets inside the ICMP. And then we have P-tunnel, which is TCP over ICMP, including HTTP or HTTPS sessions. And then ICMP-SH is reverse shell. Attacker controls the victim via echo replies. And then ICMP, this mouse, oh my goodness. It's gonna go out the window today. Yep, it is. Okay, ICMP door, which is a C2 channel using ICMP heartbeat for persistence. So those are just some tools that you're going to want to get to know, you know, as your career progresses and as you go through really these sessions probably. So most firewalls are header-only inspectors at the perimeter. So they see type 8, they pass it. They never look inside the data field. Only NGFW with DPI, which is the next generation firewall with deep packet inspection or anomaly-based SIEM rules, which will catch this. So the IDS rules, type 8, echo request only, with a D size of less than 100 will show, or greater than 100 will show a payload anomaly. Threshold is the rate limiting to reduce false positives, right? So if you're an attacker, I'm going to ask you guys this. If you were an attacker and you knew defenders were filtering on D size greater than 100, what would you do? Any ideas?
I'm sorry, I didn't catch the question. What was that again?
Okay, let's say you were an attacker and you knew that the defenders were filtering on D size of greater than 100. What would you do if you were like the attacker? Well, I think
I'm gonna, yeah, I think I'm gonna move below the 100 packets.
Right, you're going to use smaller payloads, right?
Yeah. So
Yeah,
it's
multiple
it's not
requests.
visible.
Right, exactly. Use smaller payloads with multiple requests and jitter timing. That's called layered detection, right? For layered detection. This is why layered detection size plus timing plus regularity is required. So use smaller payloads with multiple requests and jitter timing, right?
Correct.
Okay, and then we have Smurf attack, which is MITRE ATT&CK T1498.001, and it's a network denial of service, a direct volume flood. So it's like similar to a DDoS. Smurf is a 1990s vintage, but it'll teach the amplification concept that underpins every major DDoS methodology used even today. And NTP reflection, DNS amplification, and SSDP floods. So in other words, an attacker sends a packet from this, and the spoofed source is the victim's IP to the broadcast address, which in this case is 192.168.1.255, and every host on the 24th receives it and sends a reply to the victim. Hang on one second, sorry guys. I think we have someone else trying to come in now. Okay, can you guys still hear me and see me and still use your microphones? Because I don't know, I pressed the button, I think.
I can hear you.
Okay, perfect. I'm sorry, guys. I gotta get myself together here. Okay, here we go. We'll finish this one up here. So, again, where were we? The Smurf attack is a 1990s vintage, but it teaches the amplification concept that underpins every major DDoS methodology used today, which, like I said before, is NTP reflection, DNS amplification, and SSDP floods. So again, an attacker sends one packet, and the spoofed source is the victim's IP. That packet gets sent to broadcast address, and every host on there receives it and sends a reply to the victim. So 254 hosts times one reply each equals 254 packets to victim for every one the attacker sent basically. So that's the denial of service, right? Where it floods the server. So if the attacker sends at 1 megabyte per second, the victim receives 254, right? Packets, essentially. There are two required conditions in order for this attack to work. The intermediate network propagates the IP-directed broadcasts, which is fixed by RFC 2644, and no IP-directed broadcast. And then the second condition that is required is the ISP allows spoofed source IPs fixed by BCP 38- or /RFC 2827 egress filtering. So the modern relevance for now are both conditions still exist in misconfigured networks and even in some ISPs. And more importantly, the logic of Smurf is identical to NTP reflection. So a small spoofed request, a large amplified response to the victim, the protocol changes, the math doesn't, essentially, right? Like the protocol changes, but the math is still the same math. So if you were a network engineer and saw a spike of ICMP echo reply traffic with no corresponding requests, what would that tell you? Any thoughts? If you're the network engineer and you see a big spike of ICMP echo reply traffic and there's no corresponding requests, what's that going to tell you? Basically, what that means is that you're the reflector in someone else's Smurf attack. Right? Okay, let's go on to the next one here. So this is PMTUD manipulation. If there's any questions, just take yourself off the mic if you can and ask me that way. That way it just makes it a little bit easier so I don't have to keep going back and forth. Like I said, I'm going to get this screen thing figured out for next week and you guys will be surprised. So PMTUD manipulation. This is the stealthiest attack that we're going to learn about today. There's no volumetric signature, no authentication failure, no crash. The connection just basically slows down to a crawl. And it looks like a network problem, basically, essentially. Like it doesn't stop, it doesn't crash, nothing like that. No error messages, no nothing. It just goes really slow. It's big time lag time. So, and here's how it works. The host sends a large packet with DF bit set. The router, it can't forward it because the MTU is too small, basically. Router sends type 3 code 4 back, which is fragmentation needed. Here's the real MTU, essentially. The host reduces MSS and retransmits. Connection works, now optimized. Okay, so that's legitimate flow. That's how it's supposed to go, right? And now for the attack, the attacker spoofs type 3 code 4 claiming MTU equals 68 bytes, the minimum legal IPv4 size. The victim honors it, reduces MSS to 28 bytes after they honor it. So 68 minus 20 IP header minus 20 TCP header. So at that point, a 1 megabyte transfer now requires 36,000 plus packets instead of the usual 700 packets. So the connection throughput collapses, right? Crash. But here's why it's hard to diagnose. Because the support team checks the ISP link and it looks fine. The router configuration looks all fine. Application logs show slow transfer but no error, right? It's slow but it's not an error. The ICMP error messages aren't typically logged. So the attack is invisible to most standard monitoring, essentially. You're invisible. The key mitigation to the PMTUD is the TCP discovers the path that MTU itself using probe packets, never relying on ICMP. So if the victim implements PMTUD, spoofed type 3/4 messages are ignored entirely. So type 3/4, messages are completely ignored at that point. So here's my question. Should you just block all type 3 code 4 messages at the firewall to mitigate? Do you think that would work? Anybody? Well, you can't. No, you shouldn't. Why?
No.
Because sorry, go
No,
ahead.
but you have to
Someone say
validate
something?
ICMP messages. Yeah, and you don't block the type 3, but you have to validate ICMP messages.
Right. Because it breaks by blocking all type 3 code 4 messages. It breaks legitimate PMTUD and causes TCP black hole issues. So like you said, rate limit and source validate instead. So right, exactly. And then we have operating system fingerprinting. This is MITRE attack T1592.001, which is to gather victim host information, hardware, essentially, or hardware. Victim host information, and in this case, it's hardware. So an attacker who knows your operating system has already narrowed their exploit list from thousands to dozens. Fingerprinting, it isn't glamorous, but it's the step that makes every subsequent attack more efficient, right? So we have TTL 128, which equals Windows. TTL 64 is Linux, Mac, or Mac operating system. TTL 255 is Cisco or OpenBSD. The payload pattern, Windows uses like A, B, C, D, E, F, G, H, I, J, K, L, M, N, P, alphabetic and consistent. Linux uses random bytes, and Mac uses incremental bytes starting at 0 by 08. These patterns are stable across operating system versions within the same family. So they run about the same within like their operating systems. So we have Nmap -O process. It's not just one ICMP ping. Nmap sends a battery, standard echo, malformed type code probes, /code probes, type 13, which is a timestamp, and TCP probes. The collective response fingerprint is matched against 2,600 plus OS's signatures with a confidence score. Oh my goodness, my cat doesn't do this either sometimes. We're not going to worry about the demo on this right now, but I will post this and the lab as well if you guys want to run through it just on your own just to see what it's all about, because I don't want to run us short on time again. So do you guys know if you can change your operating system fingerprint? Does anyone know if that's possible? Well, you can, because there are tools like HoneyD that serve false responses, or IP tables can manage TTL values. Some security products actually randomize ICMP response payloads, but they're rarely deployed, and it's an advanced hardening measure kind of. So you'll learn more about that. So if your IDS alerts, this is for you guys to answer. If your IDS alerts on an Nmap -O probe battery, what does that tell you about where in the kill chain the attacker is? So if your IDS alerts on an Nmap -O probe battery, what does that tell you about where in the kill chain the attacker's at? Well, basically, it's at the pre-exploitation reconnaissance. They haven't even touched any ports yet, essentially. Okay, so we have detection and the defeat summary here. So this is every attack we covered is mapped to what triggers this and how to stop it, essentially, right? So reconnaissance attacks, if you recall, like ping sweep, operating system fingerprint, signature is volume and probe pattern. On the denial of service attacks, so like the ping of death, the Smurf, the PMTUD signature is size anomaly or off subnet source. I feel like we missed something. We missed it. Hang on, you guys. We did too. I thought so. No, we didn't. Okay. Okay, so the denial of service attacks, signatures is the size anomaly or off subnet source, as we said. The manipulation attacks, so like a source for legitimate message type. So, and then we have covert channel. So tunneling signature is payload anomaly and timing regularity. Every row here has an attack technique, and in a real SOC, these map to alert categories in the SIEM. So when the analyst gets an alert tagged T1018, they know immediately recon, live host discovery, look for follow-up on TCP scanning. So that'll be like when you do the Wireshark. I don't know how familiar any of you guys are with Wireshark, but like I said earlier, you're going to have to be using that quite a bit in the next sessions coming up. So structural recommendations. So let's see. The emphasis I'm going to do is on these four. So separate ICMP policies for perimeter versus internal. So different threat models, right? Anomaly-based detection, signature, because the signature alone misses tunneling and PMTUD abuse. And then host-based hardening is so disable accept redirects, enable PLPMTUD, and log ICMP, because most shops don't. That's the biggest gap, is to log the ICMP. So you now have the conceptual framework. And we have a lab, but I don't know how we're doing here on time. You can see we're almost out of time, I believe. But if you guys want me to, I can post the lab, and then if you guys want to do it, you can. And then if you have any questions, you can always ask me about it, and you can email me your answers, or we can just, I'll just post it and you guys can just have a look at it at least, right? Is that okay? Does that work for you guys?
I mean, yeah, and we can probably review it sometime next week.
Yeah, we can do it that way too. Or you guys, yeah, that will work. Whatever works best for you guys that way. I'm easy that way. I'm gonna have a look here. I think that there's a, if I can find it. Sorry, you guys, I'm like all over the map here today. Like I said, I haven't been feeling good the last couple of days. You'll see, next week is gonna be a big change. It'll be a lot better by then. But I do believe in you.